Welcome to Advanced Concepts 1 for Chem 126 about gummy bear osmosis. For today's experiment, we are going to be using 3 gummy bears of the same color, 2 clear cups with plain tap water filled about halfway full, and in one of the cups, as you can see, I am adding salt water and stirring it until the salt stops dissolving. That's when I know I have enough salt for my experiment. I'm stirring, and when you see the salt at the bottom of the cup, little salt crystals, then you can stop stirring, and then you'll take your 2 gummy bears. You'll have 3, but one is just your example, and you'll put 1 of each in each cup. The brand doesn't really matter as long as you use 2 of the same brand. So after 6 to 10 hours, mine were actually left in for 18 hours, we then remove our gummy bears from the water, and I'm just removed the gummy bear from the plain water. Now I'm removing the gummy bears from the salt water, which you could see is very tiny there. And we're going to discuss what happened with our gummy bears, and that's the original gummy bear that was my control. So let's take a minute to review what happened with my gummy bears. So gummy bears are made from gelatin and water. They start out as a liquid and some flavoring and sugar, and they're heated and cooled into a chewy, gummy solution. This is a result of the presence of gelatin, whose molecules are chain-like and create a solid matrix with strong bonds that maintains the shape of the bear, or whatever shape they're formed into. Gelatin is made with collagen, and collagen is a type of protein that is found in the bones and tissues throughout our body. The collagen used in gelatin is animal-based, and again, you can see some of the pieces that broke off in the plain water there. So what does this have to do with the human body? So the gummy bears in this lab are helping to illustrate the process of osmosis, which is the flow of liquids from a dilute to a concentrated environment through a semi-permeable membrane until an isotonic solution, that is one of equal concentration, has been reached. When we compare this process to the human cell, the solution can either be isotonic, hypotonic, or hypertonic. When the concentration of an area of low concentration of solute in the cell's cytoplasm and the concentration of the solute in the solution are equal, we call this isotonic. This means that the cell will not gain or lose any water. When the concentration, in the solute of the cell cytoplasm, if it is greater than the concentration of the solute in the solution, then this is considered hypotonic, having a comparatively lower concentration of cellular cells dissolved in liquids. In a hypotonic situation, the cells will swell and possibly burst, as you see on the left. Compared to our control gummy, you can see the size of the one in the plain water that is quite large, and also in 2 pieces over there. Okay. So finally, if the solute of the cell cytoplasm is less than the concentration of solute in the cell solution, it'll shrink or crenate, which is wrinkle and condense. And this is, as I'm pointing to, is referring to hypertonic. Hypertonic solutions have a higher concentration of solutes, which are solids dissolved in liquids. The semi-permeable membranes in the gummy bears are what allow the molecules to pass through. They actually allow some molecules to pass through, but not others, depending on the state, the hypertonic, hypotonic, or isotonic of the solution. This is because the gelatin in the gummy bears is kind of like the cell membrane of the human cell. Again, this is going back to the collagen. So since the gummy bears in our experiment are non-living, they're semi-permeable, meaning they don't pick and choose which liquids diffuse, whereas in our bodies, our cells are selectively permeable, which means they're living and are able to differentiate between various molecules and adjust to our cells' ever-changing needs. So my hypothesis for this was that I predicted that the gummy bears in the salt water would shrink in size and the gummy bears in the tap water would grow. The ones in the salt water would shrink, and they did shrink because of the salt in the water, and the ones in the tap water, well, that's the salt water there, and that gummy bear did shrink, and the ones in the tap water grew because ingredients in the gummy bears absorb water. So why, like, how did this happen? So when the gummy bear was placed in the water moved into the gelatin because there are larger molecules in the gummy bear than in the water, and the gummy bear grew bigger. When the gummy bear was placed in the salt water, the water moved out of the gelatin because there's more salt chemicals in the salt water than in the gummy bear, and the gummy bear shrank. What are the variables? The dependent variable in this experiment is whether the amount of water lost or gained in the gummy bears varies in a linear fashion. The constants are the type of gummy bears we used, the type of salt, the type of containers, the amount of water, the controllable things, the time the gummy bears have been left in the water, and if we were to have used any other tools such as a scale or measuring device, which we did not in this case. So our gummy bears spent 18 hours in both the plain water and in the solution of salt and salt water. So how this shows us osmosis in the tap water, the gummy bears expanded on the left side as the water moved by diffusion through the bear's semi-permeable membrane to reach an isotonic state where the concentration of water molecules inside and outside the bear was the same. Wow, did my gummy bear on the left expand? In fact, my gummy bear actually broke as I was removing it from the water. This may have occurred because of the brand I used, which had like sugar on the outside of the gummy bears, which created an extra infusion of water possibly, or because I left the gummy bears in for a whole 18 hours. I had seen different experiments on YouTube where people used various amounts of time, and I do feel that the longer they're in the plain water, the softer they would become, and the longer they would be in the salt water, the smaller they would become. In the salt water, the gummy bears soaked in the salt water have shrunk. Though the bear's gelatin construction will cause it to hold its shape and size for the most part, though its arms and leg nubbins are pretty much imperceptible at this point. This bear reminds me of a Lucky Charm marshmallow. So let's review what occurred and why. Imagine the gummy bear is a real living thing. It would be made up of tiny living units called cells. Each cell is surrounded by a membrane that protects the cell by keeping the parts of the cell inside and keeping other things outside. While it stops most things, water can pass through it. With the gummy bear and the salt, the water had to move out of the gummy bear to even out the concentration of water. The gummy bear became smaller with less water to fill it up. The opposite happened to the gummy bear in the plain water. The water moved from the outside of the gummy bear to the inside to even out the concentration of water. As more and more cells gained water, the gummy bear became larger as more water filled it up. So why didn't the gummy bear in the salt water get as big as the gummy bear in the plain water? And what does this have to do with us? Well, osmosis works in a similar manner in our cells as it does in the gummy bear. When we sweat, we lose water. Osmosis takes over and starts to pull water out of our cells. If we drink water, it returns to water to our cells using osmosis to balance out the equilibrium. Same goes for when we have too much salt and wake up really thirsty in the next morning. Our cells lose water to the salt in the cytoplasm of the cell because water is moved across the membrane from the less concentrated, hypotonic, to the more concentrated, hypertonic, until the concentration is equal on both sides. This, my friends, is called equilibrium.